Hello everyone. In today's lecture, we'll focus on data provenance for generative artificial intelligence. In essence, here the goal is to identify and trace how data is used in generative AI. So today's leading generative models like GPT, Gemini, and Llama, they are trained on vast and enormous datasets. These datasets include news articles, music, books, code, images, and much more. The scale and diversity are what make generative AI so powerful. They enable these models to generate everything, from complex text to photorealistic images. But these impressive capabilities also create profound risks. First, it was showed that image generative models can memorize and then generate thousands of their training samples. For example, they can generate a Harry Potter book, word by word, or face of this woman, pixel by pixel. As a result, there are now over 100 ongoing copyright lawsuits with claims of over 90 billion euros. Second, generative AI is exploited to produce misinformation and fake news at scale. This undermines our democratic processes and also makes it harder to trust the information we see online. Finally, generative AI creates data loops. Content generated by these models is published online, then scraped and reused to train the next models. In the long run, these data loops degrade the quality of models. Specifically, they amplify harmful biases from earlier models and carry them over to new models. All of these risks point to the same scientific challenge: data provenance tracing for generative AI. We must know where data comes from and also how it is used. The EU AI Act demands that we address these risks now. Article 50 requires robust marking of generated content and takes effect on December 2nd this year. Article 53 requires compliance with copyright laws and already took effect last year. So the problem is highly urgent. I spoke to my collaborators at Google and OpenAI. I spoke to representatives. We all want to break the data loops. The proposed solution is to build a unified data provenance framework for generative AI. This requires addressing three fundamental scientific questions. First, on the input side, the question is, how can we reliably identify if particular data was used to train a generative model? The second question during model training is, how can we formally define and quantify memorization? The aim is to control memorization so models learn general patterns rather than memorizing individual samples. And the third question on the output side is, how can we persistently mark generated data, identify it, and prevent its reuse in training future models? So let me start with the first part on reliable data identification. So previous data provenance methods try to identify if a single data point, like a sentence or an image, was used to train a generative model. In 2024, we made a breakthrough. It was twofold. First, we showed that given the massive scale of these models, a signal from a single data point is too weak to identify training data. Second, we also showed that when we extract and aggregate large number of signals per sample and across a dataset like a whole book, then we can provide strong enough evidence to reliably identify training datasets. But we really need to also go beyond such result to other models and also to provide these statistical guarantees of data being used to train a given model or not, even in the case of smaller data sets than just, for example, the whole book. So let me first go into this aspect of how we can detect data sets for LLMs. So now we'll focus on the aspect of how we can detect if datasets were used to train large language models. Here we will focus on the LLM dataset inference method. This method consists of 4 stages. We will go through the stages one by one. So first, victim, who probably might have some data used to train an LLM, approaches an LLM provider. The victim's data consists of the suspect and held out sets. A victim claims that the suspect set of the data points was potentially used to train the LLM. The held out set is guaranteed as not used to train the suspect model. This can be, for example, in the case of an author like J.K. Rowling, that the suspect set is a Harry Potter book, and the held out set, for example, is a draft of articles, blog posts, or maybe some unpublished books by the same author. So here, the important part is that the held out set is from the same distribution as the suspect set. So both sets are divided into non-overlapping splits, partitions, A and B, where A is for training and B is for testing. So the test that we want to perform is to answer the question: was suspect LLM trained on the suspect set? And the assumption is that these both sets, they should be from the same distribution. So when we carry out the test, by ensuring that we do have the same in-distribution data sets, suspect set and held out sets, then we don't have any, for example, distribution shifts that might skew the result. So in the second stage of our method for LLM data inference, we extract membership features. So here we take these splits A from the suspect and held out sets and pass them through the LLM to obtain their features. So these features are scores generated from various membership inference methods for LLMs. So here you can, for example, think that in this scenario that we from the given LLM can obtain the outputs, and then from the output we can, for example, estimate what are the token probabilities. And then if we observe that our LLM actually is very, very confident on predicting the next tokens from our suspect set, then this might be an indicator that the LLM was trained on this data. So we extract many such features called membership features from LLM. Apart from the token probabilities, also features can be, for example, based on the aspects like was the given data set after generation similar to what we have in our suspect set. So if, for example, we give some prefix, generate the rest of the text, and then after generation we check, for example, by embedding this text, if these texts actually are similar. So once we learn these suspect and held out features, then actually in stage 3 we learn correlations between features and their membership status. So we train a model using the extracted features to assign label 0 to suspect features and label 1 to the held out features. So the goal is to identify useful membership inference features for a given model and dataset. So here the model is expected to produce low scores for the suspect features and also higher scores close to 1 for the held out features. So then we use the B-splits of the suspect and held out sets. We extract membership features from them using the suspect LLM, and then we obtain the aggregated confidence scores using the previously trained scoring model. So here we apply statistical test on the obtained scores. For the suspect data points that are members, their confidence scores should be significantly closer to 0 than for non-members. Then we perform the final step. So we use the B-splits of the suspect and held out set. We extract their membership scores for the suspect LLM to obtain the features, and we compute the scores using the scoring model and aggregate these final scores. Then we apply a statistical test. For example, it can be t-test or a test based on the e-values, and then use the obtained you'll obtain scores to compute the statistical level. So if the statistical result is significant, then actually we give a verdict that a given data set was used to train a model. Otherwise, the data set is marked as being non-member, meaning that was not used to train a given LLM. Now, this method up to now works if we have access to the held out set from the same distribution as the suspect set. However, this is a strong assumption, and such a set, like the held out set with the, let's say, drafts of our previous papers or books, might not be available in practical setups. Therefore, we also have to think, how can we potentially generate or provide this held out set in a different way than just requiring from the given author to provide it. Additionally, it might be also the case that in some cases an author might potentially be malicious and try to accuse a given model provider of training on the given book or publication or blog post, and then provide held out set from different distribution, and this would cause the shift in the scores and potentially provide as a false positive. So here the main question is, how could we really generate this held out set as the maybe third party that is supposed to verify if the given suspect set was truly used to train a given LLM. Okay, so now we will show how to generate this held out set from this suspect set. So first we take the snippets from the suspect set and segment them. We divide them into prefix and also corresponding suffix. Having prepared this data, we train a generator model to complete the suffix given a prefix. So once we train this generator, we use it on the second split of the suspect set to generate the held out set. So in this case, what we observe is that we can actually use powerful generators for, in this case, language, to provide us the completion of the given, for example, sentences. And this completion can be trained on one part of the suspect set and then provided for the another part, split A2, for the suspect set. So now, how to distinguish between the distribution shift versus membership signal. So the text classifiers are trained first on the suspect set and held out set. So here the goal is that we would like to understand if on the level of text only we are able to differentiate between this suspect and held out set. Now, what if we also use another signal, not only from the text itself, but also from the model? So in this case, our member classifier does not only use the features of the text, but also signals from the LLM. So now we also additionally incorporate in our method the knowledge from the LLM. So we here intuitively check if the LLM has some knowledge about our suspect set. And here for the final statistical test, we set the following hypothesis, which is alternative to the null hypothesis. So the membership classifier, noted here as a member, should only outperform the text classifier, which is also here in the inequality denoted as text. So these different classifiers, member versus text, they should differentiate between held out and suspect set differently only if the suspect set was seen by the given suspect model, in this case this LLM. So in simple words is that if the suspect set was in the LLM training set, actually this difference between the scores, this member of the held out set versus member of the suspect set, so the scores for the member classifier will be much different then the scores for the text classifier, which was trained only on the textual features. So here the intuition is that the signal in the model itself would skew the member classifier result for the suspect set compared to the held out set. So here, remember that for held out set, we set the scores to be close to 1, for a suspect set close to 0. So if the suspect set was seen by the LLM, actually these scores would be very much different and on average close to 1. For the text classifier, if the classifier was actually trained just on the text features, so of course in this case we don't have any signal from the suspect set, and actually these features from the held out set and the suspect set should be roughly the same. So here we wouldn't have any differentiation between the held out and suspect set, and this value here would stay close to 0. So the expected difference between member classifier on held out versus suspect set would be significant compared to the, so much bigger compared to the difference between the scores for the text classifier. Now, so in this case, we showed how to generate this held out set. But are there any other approaches how we can actually create this held out set than just trying to generate it from scratch? So another solution to this problem of generation of the held out set, also we developed a method based on the natural identifiers. So these are natural random strings, for example, like URLs or cryptographic hashes like MD5 or SSH keys that, for example, you use to connect to servers remotely. So these strings actually, they occur quite frequently and naturally in models' training data. So these natural identifiers, we in short call them NIDs or needs. These needs have known generation functions that we leverage to generate an unlimited number of held out or these non-member data points from the exact same distribution as the natural identifiers, these needs. So what is the here intuition is that if in the large corpus of text, for example, we also use code from GitHub to train LLMs, then in many of these code bases we see these URLs, we see, for example, SSH keys, and actually here the idea is to use them to actually generate this held out set. So here is an excerpt from Refined Web, Dolma. So this is one of the data sets used for training Olma models, and we have this MD5 cryptographic hash in this text. So we know how to generate these MD5 cryptographic hashes, and now what we actually do is that we treat actually this specific hash as our natural identifier, and then to create the held out set, we also replace these natural identifiers with so-called GID. So GID is a generated identifier. It's just a way how to generate and not just take an identifier from the text. So in this case, we just generate a new MD5 cryptographic hash and replace that new one with the previous natural identifiers that actually were in this text. So we go from these natural identifiers to generated identifiers to create this large amount of held out set. So just to have the clear picture, natural identifiers are structured random identifiers that naturally occur in common LLM training data sets such as this Dolma. Also there are other, like for example Pile. And then in this suspect set, potentially we replace the natural identifiers with generated identifiers. So these are generated identifiers from the exact same distribution of natural identifiers. And here we have the full example with this Refined Web. The question is, how can we use this new held out set for our identification of the training data sets in LLMs. So this is quite natural. So we have this aspect set with many of these natural identifiers. So for example, let's say that this aspect set actually is GitHub repositories, and then we have many of these natural identifiers like SSH keys, and then we just simply replace them with generated identifiers like generated new SSH keys, and this actually forms our held out set. And now let's consider what are the properties of natural and also generated identifiers. So identifiers, in short IDs, are produced by sampling first randomness, and we call it Z, using a generator function W. So we have this value V being W of Z. So we use the generator function W with some randomness to generate this value V. You can think about W, the generator function, for example, being the generator for SSH keys, and Z is some randomness that we just take. For example, it can be that we take the current date, we just hash it, and this can be one of the ways how to provide randomness. And so V becomes our natural identifier that naturally occurs in the real datasets, like in this Dolma or the pile. Property 1 of an IDs is that a priori this ID V is equally likely to be generated and published because it only depends on the source of randomness. So here the idea is that if I generate a SSH key now and put it into my GitHub repository, then of course it should be public SSH key, then it doesn't matter, like if this was generated today or maybe 2 days later, the values should be some random values. However, if the model has seen my training data, in this case my repository from GitHub, with my public key published in the repository, and the model might learn exactly this specific sequence of characters for this an ID. Now, once I want to test if my data was used to train this given LLM, I can just generate ad infinitum, as many as I want, additional GIDs, this generated SSH keys, and then just compare if this LLM really differentiates between my specific identifier, my specific SSH keys in my GitHub repository versus all other possible generations of these SSH keys. So the set of all possible IDs from the generator W, so we call it like W upper V, is just all possible generations that we can have from the generator W. So then, if we want to generate the new identifiers, so GIDs, we sample simply fresh random inputs from Z prime, generate new identifiers V prime, and actually they form our GIDs. And then there's also this problem that it might occur that in some very, very rare cases, we generate the same V prime as we would generate V, but this basically happens with very, very low probability. So here, thanks to this randomness of these generators like SSH keys or MD5 hashes, these collisions are of extremely low probability, so we don't have to really, in practice, care for them. And property 2 of these identifiers is that identifier space V, so all possible keys that we generate, is extremely large. So we can really, in this case, provide as much of this held out set as we want. There is no limit on how big it can be. Now you might ask, okay, so if I have these specific identifiers in my data, then I can imagine that I can use generator function to generate ad infinitum more these GIDs. But how does it work if, for example, a given data set does not really have exactly these identifiers that occur, for example, in a GitHub repository? So what if we have some, in this example, some math problems, and we just have some numbers that are not generated randomly, but they have specific meaning? So how can we extend this idea of natural identifiers and apply that to more maybe natural text, something that we see on daily basis? So actually here the idea is that we can still design task-specific natural identifiers. So the example here comes from a GSM-8K dataset, which is just a dataset of simple math problems. So in this example, for one of the samples from the GSM-8K dataset, you can treat the number, in this case 48, and all derived quantities such as 24 and 72 as this need variable, this natural identifier variable, and just simply substitute them with different numbers as generated identifiers in a consistent way. So for example, if Natalia in this case sold clips, and in this first case natural occurring text was 48, then to generate this her set we can just change this to 46, and then also we have to follow up with this number, this variable, in the remaining text and replace these numbers. For example, if Natalia sold 46 over 2, then it's 23 instead of 24. So we just set these variables and we just update them according to specific new variable that actually we chose. In this case, it could be also randomly. And then we kind of verify. And then we verify if the model learned our specific example of 48 and following numbers, or the model didn't really see such an example, that it's not really in any way attached to the value 48, but can generalize to any value like 46, and there is no difference in model behavior between specific values of these clips that Natalia was selling. So now let me show you how to perform post hoc method of inference and using the natural identifiers. So we start from the some LLM that was trained on a large amount of data. Then we extract natural identifiers and also then generate these new identifiers. So as we discussed, given suspect set, so for example, one might accuse, let's say, one of the big companies of training on my code. Then we take my code, we extract from my code all of these SSH keys, MD5 hashes, and specific random strings. And then for these identified natural identifiers, we generate the GIDs, the generated identifiers. And then how do we audit if the given data set was used to train this LLM? So we take the sets of these needs and GIDs. So we just have this all the possible values for the natural identifiers, and then we check, we rank how model really performs on this given needs versus GIDs. So given the resulting trained model and the filtered needs with corresponding GIDs, we seek as an auditor to infer for each set of this V sub I, so all possible identifiers, which sample was the need. So to do so, the auditor ranks the samples in V sub I from the most to the least likely natural identifier, or in this case an ID candidate, and then prediction is considered correct if the true natural identifier appears among the top R sub I ranked samples, where R sub I is a predefined threshold. So how can you think about that is if we have this NID being a SSH key, and the LLM in this case was highly influenced by the SSH key, so we can basically see as an auditor rank that probably this specific natural identifier, so my SSH key, was actually in the model's training set. So the rank is consistently very low for my specific identifiers. Actually, this indicates that the LLM was trained on this data. However, in the opposite case, if my natural identifiers, so my SSH keys or MD5 hash values, they are not ranked on the top positions, then somewhere randomly in this ranks, and actually this indicates that this model probably with high probability was not trained on my data. Okay, so up to now we discussed how we can detect data in generative models. Now let's go to the next topic. So after a model saw some input data, model trains on this data. And here in this lecture we'll cover this aspect, how models really memorize this data and how we can really find out which samples models memorized during training. So before we go into the details of how models memorize the training samples, we'll focus on the new type of image generative models, which are called vision autoregressive models, in short VARs. We can also call them image autoregressive models, in short YARs. And these actually models, they generate images which is so-called scale by scale or resolution by resolution. And also within the given resolution or scale, they also generate these images token by token. So how it works is that you can think about starting from resolution R sub 1, and this is your initial idea how the image could look like, and then R2 is a bit more refined, R3 is maybe a bit more pixelized, and then in R4 you can see the shape in this case of this parrot, and then in R sub k, after many of these resolutions in the last scale, you have a very detailed view of the given in this case animal. So in principle, here we want to adapt the generation techniques from large language models that generate text token by token to the generation also of images. So we want to generate these images also in a kind of sequential way, token by token, within the given scale. So there are already two training steps in VARs. In the first step, we have to train a multi-scale vector quantized autoencoder. So the autoencoder model starts with an initial image that is then transformed to a latent, and then we reconstruct initial image from the latent. So we take the initial image, encode the image, then the encoded image is turned into scales or all these resolutions with many tokens per scale. Then the scales are unified into an embedding, and then we do the decoding. So I will explain step by step in detail in the next few slides how we really perform this stage 1 of training this multi-scale vector quantized autoencoder. So once we train the autoencoder, the next stage, number 2, is to train the VAR transformer. So this is basically an autoregressive model which is trained on tokens. So here I'll also describe that more, how we generate these tokens for images one by one. So let me first start from the training of this multi-scale autoencoder called vision quantized VAE on images. So the stage 1 is to train a multi-scale, this vector quantized versional autoencoder, to encode an initial image into k-token maps. So we have these k-token maps, so we call them resolutions. This is why you have this denoted as R. And we have this upper R, so all possible resolutions for the given image from R sub 1 to R sub k. So here we have initial image on the left hand side of a cat. This is image from the ImageNet dataset with dimensions 3 by 256 by 256. So we have this relatively high resolution image, and then encode the image using convolutional neural network. So these are basically conv layers, usually a few of them, like 4, to go from the pixel space to the latent space. So actually this latent space feature map is of dimension 32 by 16 by 16. So we here operate these models in the latent space. Once we find the latent of the given image, and actually we tokenize this latent. What it means is that we, in these models, for example in VAR, have a codebook. So codebook consists of, in this case, 4096 entries. So this is the vocabulary size. And each entry in this codebook, you can think this codebook being a dictionary. So each entry in the codebook has 32 float values. And these float values basically represent a possible token for the image. So given this encoded latent, we just quantize this latent into many such tokens. So then we have this reconstructed feature map. So how do we reconstruct the feature map? Is that so ultimately we operate on the index from the codebook. So once we identify for the feature map all the possible tokens, and we just only keep the index of the token, and we don't store the whole entry from the codebook. However, if we have the tokens, for example, we generate these tokens, so we have the bunch of all possible tokens, then actually we just go to the codebook, we replace each token with this specific entry, and then this actually is recreated, reconstructed feature map. So now we have the continuous space again, and then we do inverse of the first encoding, so we decode the image using also convolutional operations to the, in this case, reconstructed image. So the goal in this process is to train the whole pipeline of encoding, tokenization, and decoding based on the input-output image to minimize in the output image the reconstruction error. So once we have this VQVAE trained, then actually the next step is to prepare this VAR transformer, these autoregressive models, to generate the tokens. So actually this model is usually associated as some transformer. So this is the way how to actually perform this autoregressive generation of tokens. So here we start from some start token, and this is the input to the VAR transformer. We have the expected resolution that we have as a ground truth, so R sub 1, and predicted one by this autoregressive VAR transformer. So the predicted one is denoted as R sub 1 hat. Then we just compute the cross-entropy loss between the R1 and the R sub 1 hat, so this expected and predicted resolutions, and this cross-entropy loss is simply used to update the parameters in the VAR transformer. Then we proceed to the next resolution, resolution 2. Again, here we use the paradigm of generating these tokens one by one. So we take the previous, in this case, ground truth token R sub 1, this resolution, and then we generate R sub 2 hat. So this is predicted by the VAR transformer, and we compare with the, again, ground truth, so expected R sub 2. We compute cross-entropy loss, and this cross-entropy loss is used to backpropagate through the VAR transformer to train it. And we continue this process in this way until we reach the last resolution, in this case R sub k. So now we are ready really to discuss how the models memorize training samples and how we can really extract which samples are memorized by these models. So here we consider these image autoregressive models, also more than just one, and our main focus is given a model, how can we find out how can we find out which of these training samples actually was used to train the model. So we start again with our encoding, and given image, we encode the image to the latent space, and then tokenize this latent space, so this feature map, into individual tokens. And then we also take our autoregressive model, the VAR transformer, and compute the predicted tokens. So you can think about that we give to the model some prefix, and the model VAR transformer is supposed to generate as the next resolution, and we just compare the generated resolution with what is the ground truth. So here we compute distances between the tokens. So is predicted token close to the ground truth token. We identify then images that potentially might have been used for training by identifying these images that actually have the smallest distances. And the next step is to now take the given image with its prefix and then just fully generate the next tokens until the last resolution for the very, very small prefix tokens. And here we, after generation, we decode this representation to the final pixel space images. Then we compute distances between the generated images and the ground truth images, and what we find is in many of these image autoregressive models we can extract hundreds of memorized samples. So for example, for the model VAR-D30, this is one of the VAR transformers, we are able to extract 698 images. So this means that 698 of these training samples were almost verbatim memorized by the model. And to give you some more intuition, so when do we really define this as being verbatim memorized? So we can give to the model a few initial tokens, for example, up to 30 tokens, and the model then generates thousands of the next tokens, and then after this generation, we have the generated image, and then we see that this actually image is one of the samples from the training set. These are examples of the images that we identify as being memorized verbatim in these image autoregressive models. So in the first row we have the original training samples, training images used to train the models, and here in the second row we have the extracted images using our method. So what we observe is that qualitatively these images that we extracted are very, very similar to the training samples. So then we observe that the generative models can literally memorize training samples, actually then can generate them. So then the question is, if we have sample which is generated versus sample that is natural, how can we really differentiate between which is which sample is natural, which sample is generated? What's more, same is for LLMs. We don't know if the given text actually was generated by a model or maybe human created. So nowadays this is a big issue. How can we really differentiate between these different natural versus AI-generated content? And here, one of the ways how to solve the problem is by applying watermarking. So we will start from the large language models, and then we have a brief really intro to how language models generate text. So this is in a so-called also autoregressive manner. So we generate this text from LLMs token by token autoregressively. What it really means autoregressively. We have first this as the initial, in this case, word, pass through the LLM generates the next word being is. Then actually what we do is take this is and we put it as the prefix and then again do the prediction on LLM to predict the next token. Here, internally in the LLM, we have the same as in this YAR models, this var that we have vocabulary of size 4096. Here we also have vocabulary for LLMs, but actually much larger. So in LLMs, this is not exactly word. We have tokens for the vocabulary. Vocabulary size in LLMs is much bigger. Can be in small models like 50,000 tokens. For the bigger models, 200,000 tokens or more. So this becomes really large vocabulary list. And here, in simple terms, what is really this vocabulary is all possible tokens that model can generate. So given this prefix tokens, this is, then the model is supposed to generate the next token. So here we give a couple of examples, what could be the next tokens, or in this case words, for example, word fine, great, nice. And then after the colon, also we specify what is probability of predicting the given token. So given these probabilities, then a model can decide based on the, for example, like top K selection, meaning that we select the top, in this case, token, or we just take top k tokens and then generate randomly one of them. But this is one way how to do it, by just taking the most probable token that we have in the vocabulary. After this, this is words. So usually one of the tokens with the highest likelihood, in this case highest predicted probability, is chosen as the next one. Okay, so now the question is, how can we really watermark the text in large language models? So this is a very simple way how to generate tokens in LLMs, also by providing some watermark signal. So we divide the vocabulary, this large list of all possible tokens, into so-called red and green lists, or green and red tokens. We usually divide this vocabulary randomly. So we just choose some random number, we just flip a coin, and then basically we for each token we decide if this is green or red token. Now, for the generation, what we really want is that we want to generate actually only the green tokens. So for the normal non-watermark text, the number of red and green tokens in the generated content actually is equally likely. The same if you would basically change from the generated content to the natural content, for example, to my text. And if you read my text, probably you won't find any sign of too many green tokens. So usually you would have the same number of green and red tokens. However, if you have text which is generated using this method, then actually you have many more green tokens. They are much more likely than the red tokens. And this is an example of how this text looks after first no watermarking. So the LLM didn't bias the token generation to the green tokens, and also with watermarking. So for the non-watermark case, what we can see is that if we then label these tokens as red and green, then roughly we have same number of green and red tokens in this text, which is non-watermark text. However, if the text is watermark, then most of these tokens actually are green. So as you can also see, not all the tokens are red. And why is that? Is because we nudge the model to generate the green tokens, but we don't force fully the model. Meaning that if we would force model, then maybe actually in this case the quality of the text would be highly degraded. But we don't want that. We just want to bias the model so that there is significantly higher number of green tokens in the generated text compared to the number of red tokens. So here, given our small dictionary with tokens being fine, great, and nice. So in the previous case, we generated the token fine because it has the highest probability. However, now the token fine is on the red list, so the LLM is not supposed to generate this token. So the LLM just uses the next token that is in the green list with the, in this case, a higher probability of 0.04 and generates this token instead of fine. So the final here outcome would be this is great if we use the watermarking instead of this is fine without the watermarking. So let me just describe more how we generate this text with watermark. So we here have the algorithm for the text generation with hard red list. So hard meaning that we just always take a token from the green list. So we first get the probability vector. So for each token we have the probability as we saw in the previous slides. And then we use the previous token to generate a random number. So this is used to split the vocabulary into these red and green lists. And then we sample tokens. In this case, because of the hard red list, we sample the tokens only from the green list. And then once we want to find out if the given text is watermark or not, we perform statistical testing. So the main question is, are green tokens in the text significantly more likely than random chance? And then if it's the case, then actually we mark this text as being watermark in the in the case that this actually text was non-watermark, then basically we have same number of red, okay, non-significant difference in the number of green and red tokens, and the text is marked as being non-generated, or non-watermark in this case. So now we'll move on to how to watermark images. So here the question is, how can we detect if a given image was generated or not? In many cases, it is really hard to distinguish between a natural and generated image. So what is the solution is actually also to apply watermarking. So we apply watermarking to images, and then we detect if a given image actually contains the watermark or not. And then if the image in this case is watermarked, then actually we mark the image as being generated. So here, before we go into the aspects of how we can watermark image and generative models, we'll have a very short crash course on diffusion models. So we denote them as DMs, and then diffusion models really generate images from noise. So here we have the initial noise. We start this generation in diffusion models from such noise, and then at some point the generative model, in this case diffusion model, can provide us with a nice image, in this case of a cat. Now, how do we train these diffusion models? So actually it is based on the predicted added noise. So we have here an image of a cat in the forest. We add some amount of noise to this image, and then we ask diffusion models to predict what was the noise added to the given image. So then the predicted noise and the added noise are compared. So for example, we can compute any loss function like mean squared error between the predicted noise and added noise, and this difference can be served as the loss to backpropagate for the diffusion model, and then train the diffusion model to predict what kind of noise was added to the image. So here, how do we then generate images starting from a random noise? So we have this random noise generated at the very beginning, and we also have a prompt that conditions how the diffusion model should generate the images. So we give to this diffusion model the prompt a cat in the forest and just this random noise. Then this a cat in the forest is just called a prompt. So this is the part that is provided for the diffusion model to condition, to guide the diffusion model what to generate. And then the diffusion model actually predicts some form of noise. Then we compare the added and predicted noise. We subtract the predicted noise from the added noise, and we have some denoise, like first step of denoising. So we here still already see in this blurred image that there is some there are some pixels that would represent probably this cat in the forest. Okay, so now once we know a bit more about how diffusion models generate images, now we can move on to the next important topic, which is how can we watermark the images generated by diffusion models. So here we'll discuss the latest Serum watermark, and then Serum stands for Simple, Efficient, Robust, and Unifying Marking for diffusion-based image generation. So first we add the watermark noise to the initial diffusion generation noise. So here how it operates is that the diffusion model, as we learned, just starts from some initial noise and then denoises this into proper image. And here for watermarking, what we actually add is additional watermark noise. So this is in this case another chosen noise that we just here concatenate. So we just added the initial noise to the watermark noise, and actually this is the starting point for the diffusion process to diffuse, to denoise the final image. So here we, in this case, do that in the LDM. LDM stands for latent diffusion model. So we don't operate with these models in the pixel space, but we operate in the latent space. So once we go from the pixel space through the convolutional layers, through the encoder to the latent space. So once we have this setup, what we can actually do is to train the watermark detector. So how it works is that we can generate some of these images with just initial noise for different process, and some of them with watermark noise. Watermark detector is supposed to differentiate between these images which were generated starting from only the initial noise versus the images that were generated starting from the also watermark noise. Then once we have this training for the watermark score, and also we know how to basically embed the watermark into the generation process, we can inject this watermark to every possible new generated image, and once we decode the image, we just have standard one of the images that these models can generate. And finally, the aspect of detection. So once we see an image, how can we classify a given image as being watermark versus not watermarked? So given the image, in this case a woman probably in a chemistry laboratory, we just encode the image into some latent space. So this is this LTM, and in the latent space in this LTM we actually use the watermark detector to then give the watermark score. So this is how we embed the watermark in the latent space, and how we also detect the watermark as well in the latent space. Now the injection of serum is relatively simple. So we set the watermark noise W once per user to values drawn from a normal unit distribution. You can also set this W initial watermark noise even per a given model. Then we inject the watermark noise W in the latent space by substituting eta, so this initial diffusion noise, with eta prime. So eta is also drawn from the normal unit distribution every time an image is generated. So eta is always random, so for any generation eta is randomly generated, whereas we keep the watermark noise fixed. Now the parameter alpha is controlling the balance between watermark detectability and image diversity. So if we set alpha to be high, this means that W is dominating the term eta prime, then actually watermark is strongly embedded into the image. This might, in some cases, if this alpha is very high, equal 1 for example, then we have only static noise for different process, and of course this will limit the diversity of generations. However, here we set alpha in the way that can balance the quality of generations and the diversity versus the quality of versus the watermark strength. And now Serum is also training a lightweight watermark detector. So here the L sub W is the loss function which is responsible for training the watermark detector. In this case, the detector is denoted as F to produce high confidence scores when watermark noise is added for image generation. So this first term minus log f of x star serves to identify watermark images x star. The second subterm is minus log of f of this tau of x star m. So this is for watermark images perturbed with a random image transformation tau or t sampled from an augmentation sampler. So this is just to add some augmentations to the given image, to also make sure that the watermark is detectable even if we perturb the image with some transformations. It can be, for example, Gaussian noise, or we can, for example, compress the image. And then in this case, this parameter m is number of samples that are perturbed to reduce the computational overhead of dynamic augmentations. And also m is the hyperparameter which we can basically set. So if m is small, then actually we don't have that strong robustness of our watermark detector against the transformation of the image. However, we have to balance that so the m is large enough so that we do have enough of this robustness of the watermark detector. Now, what is important is that for the sampler's design, we also adapted prioritized experience replay to prioritize the perturbations for which the model performs poorly. So here we want to just train the watermark detector on specifically these images, which after transformations can have this watermark removed. So we want to train our detector especially to be robust against these hard transformations. And we prioritize in the training these hard augmentations by using a prioritized experience replay. And the final subterm is a minus log of f x star sub t. So this is for pre-computed transformations. So doing the prioritization with the prioritized experience replay is relatively costly, but you can also just pre-compute many augmentations of the given image and then just take the pre-computed augmentations. However, in this case, we don't have this adaptivity. We don't have this dynamic option of selecting this best transformation and generating the best transformation that would fool our detector. So this is also another term that is used here to lower the burden of generating these transformations during the training process of the watermark detector. And also we have the similar loss, but in this case for detecting the clean images. So here no watermark is added, and this is just analogous to the part with the watermark added. And the final function is just a combination of the losses for watermarked and clean images. So Serum supports multiple users seamlessly by assigning to each user I a unique subset S sub I. So this S sub I is from 1 to m of k-normalized noise patterns. And this is also together with a corresponding user level detector score d sub I of x. And the watermark injected for a user I is obtained by combining all of the patterns belonging to that user as a product of the detectors per pattern. So the overall watermark score for a sample X is defined as the maximum score among the detectors for watermark patterns. So the user associated with the given watermark is simply the user whose detector returns the highest score. So here the idea is that we set this specific watermark noise, in this case noises, per user. So we inject for the given user, for example, in this case k specific noises, and also we detect if the given image actually contains these k specific noises by using these detectors d sub I. Okay. So now we can also discuss how we can actually watermark not only diffusion models but also these vision autoregressive models that generate images scale by scale. So in the previous part in memorization, actually we saw that actually these images are generated scale by scale, and then within a given scale actually we have tokens. Now the state of the art of the image generation was achieved by the infinity model that extends the next scale prediction from token by token to bit by bit generation. So this bitwise generation enabled the scaling of the tokenizer vocabulary size, and this was almost like infinity, starting from 4096 tokens for the VAR model. Here the tokenizer is of size to the power of 64. So it's even much bigger than tokenizers that we actually have for language models. So this infinity model actually set a new record for autoregressive text-to-image models, outperforming even top-tier diffusion models. So to enable the identification of content generated by bitwise image generation models, we introduced a watermark which is called bitmark. So the method embeds a watermark directly at the bit level during the image generation process. So the bitwise watermark subtly influences the bits to preserve visual fidelity and generation speed while remaining robust against a spectrum of removal techniques. So the watermark embedding is designed to the bitwise generation. So we embed this watermark directly on the bit level in this autoregressive generation process. So first, we separate the list of all bit sequences, in this case 2-bit sequences that are possible, so 0, 1, 1, 0, 1, 1, and 0, 0, into red lists and green lists. So actually this is similar to how we do it in the language domain. So here, let's assume that the previous bit, so the previous bit was here 1. So for the next bit prediction, the bit 1, we just take the logits from the model. So model predicts what should be the next bit. So L sub 1 is logit for bit 1, and L sub 0 is the logit for bit 0. So we just here compute the softmax for the bit 1. We also do the same for the bit 0. So we compute this based on the logits of the bit 0 and bit 1. And actually the generation of the watermark, also similarly to LLMs, softly nudges the model to generate more of the sequences, the bit sequences from the green list than from the red list. So for each next bit prediction, if the bit can complete one of the bit sequences from the green list, in this case green list is denoted as G, we add a small bias delta to the logits for the green bit, in this example for bit 1. The next step is to detect the watermark. So to do so, we perform a statistical test. Here it is based on the z-test, and we test our null hypothesis that the sequence of bits is generated with no knowledge about the green and red lists. So if the null hypothesis is true, then the computed number of green list bit sequences, denoted as upper C, has the expected value of gamma times t, and the variance gamma times 1 minus gamma times t, where this gamma is the proportion of green lists and usually set to 0.5. And we reject the null hypothesis and detect the watermark if this z-score is above a predefined threshold, for example, threshold of 4. Now the question is, what if I do not watermark outputs from a generative model? Can we still detect that a given image was generated? Can we still trace a given generated image back to the model that produced it? So these were the questions that we asked, and then we also found answers to them, in this case for these image autoregressive models. So actually we carried out the data provenance on the token level. Given a natural image, we find the sequence of tokens for this image shown in green. Since the tokens of the given model are sampled from the codebook entries, the codebook in this case acts as a key to distinguish the token representations of generated images from those of real images. So we also analyze the initial tokens showed in red that led to the generated images, and then we found that the tokens shown in red for generated images are closer to the codebook entries than the green tokens that represent natural images. And actually this was the key to identify generated images by not watermarking these images. So now how this process works. So here we start from the generation process. We describe that from the perspective of a autoregressive model. So we have this model that generates tokens into the token map. So we have this internal map that is then dequantized, meaning that we take the specific codebook entries, so float values, and then this actually tokens represent a feature map. We decode this we decode this feature map into the generated image x sub z. So here the notation is that upper T is the set of tokens that are generated from the AR, so autoregressive model that generates these tokens T sub z token by token. Q inverse or Q minus 1 is Q to the power of minus 1 is the inverse of quantization, meaning that for each token expressed as the index, we just expand this token to the codebook representation, so a long vector of float values. And this for each token, these vectors form our feature map, and we decode using convolutional layers this internal representation, so the latent space, into the pixel space generated image x sub z. Now we also can do the inverse process, so we can go from the image x sub z to the tokens. So we do inversion of the decoding process, so this d to the power of minus 1. So we go back to the feature map, and actually then from the feature map we can just quantize this feature map into the tokens, so t sub z. Here we also show the inversion process, but visually, so starting from the image, through the inverse decoder, the inverse, we obtain the feature map, and then we just identify if this feature map entries, if they come from the codebook. So what is the main way how to identify these generated images is using, in this case, quantization loss. So intuitively, this quantization loss should be lower for generated images. How do we compute this loss? So we have our input image, we decode the image through the inverse decoder to the feature map, then we quantize the feature map into the tokens, and then we requantize the tokens into the feature map, and then we compare the requantized feature map with the initial feature map for the given image. And this difference between the feature map f and requantized feature map we call quantization loss. So it's computed as the L2 distance between the feature map f and the requantized feature map f sub z, and this distance f versus f sub z is relatively small for generated images versus natural images. And this quantization loss was one of the signals to detect generated images without watermarking them. So this is the final refinement. How can we further improve the detection of the generated images? So it occurs that we can further fine-tune the decoder. So we can create better inverse decoder to have a more precise feature map that actually reflects the feature map used for the generation. And by decoding inversion training, what I mean is that here we start from the feature map of the generation process. We decode the image to some generated image x, and actually we do the inverse decoding to go to the reconstructed feature map, and we compare the feature map f sub z with this reconstructed feature map, and we check how far they are, and actually this is our loss function to then train this inverse decoder d to the power of minus 1 that is more faithful in recreating the feature map that actually was used for the generation. Okay, so we covered this past work on these three aspects of data provenance, and now let's just look into the future and then try to identify what is the next step to provide strong data provenance for generative AI. So current methods operate at two extremes. They either test individual samples or entire datasets. But single samples are not enough, as we saw in the previous slides. For datasets, we do not know in advance how much data is sufficient to obtain a required significance level. In some cases, the signals from a given dataset are enough. In others, they are not. So instead, we need an adaptive evidence accumulation framework and it should work as follows. So we start with a small batch of data, for example, a few sentences. We extract informative signals from these data points and compute an initial evidence. If the null hypothesis holds, meaning that data was not used during training of this model, then the evidence should remain small. But if the data was used during training, then we can collect more data and stronger signals to accumulate more evidence until we reach the required significance level. So the final outcome should be a method which is practical and can provide us valid statistical guarantees at any point in the process. What's more, generative models are not only trained on large amounts of data, they also generate large amounts of data. So here what we want to do is to unify the identification of both training and generated data into a statistical framework. So here we also have to design specific features, or we also call them signals, that can be extracted from the laws, token probabilities, or internal model activations. And these signals should form signatures of the data and provide us with strong provenance evidence for the statistical framework. So now the question is, how can we identify and extract the strongest provenance signals that are memorized by the models? So currently there is still a scientific gap in understanding fully memorization in generative models. So prior work only considers two categories of memorization. We have first so-called unintended memorization, where models memorize individual samples verbatim. So here in this case we have this famous memorized phase of the Graham lot that was memorized by diffusion model. And other form of memorization which we actually also want is so-called intended memorization, where models learn general patterns. However, as of now, what we want to still achieve is to have new approaches that can actually measure memorization of the samples during training as a continuous score. So we would like really that for each sample we can identify if a sample is highly memorized, having high score, versus low memorization, so sample is not memorized. So crucially, once we can measure memorization, it is also controllable. So we can then design methods that control how much individual training samples are memorized and which of these patterns drive this memorization. So now the question is, how can I identify and extract the strongest provenance signals that are memorized by the models? So current watermarking methods that basically would operate only on the very single image and adding separate noise per image. So if you go back to the part on serum, if you wouldn't have the watermark specific noise, static noise for the generation, and actually these watermarks are usually ignored when we train a new model on this watermark data. And why is it happening is because the watermarks do not form, in this case, useful patterns for the model to learn, which means that if I have very random pattern for every single image, then these random patterns, of course, are not picked up by model 2 when training on the watermark data. So here, what we really want is to have radioactive learnable marks. So these marks should be detectable when a new model, in this case model 2, is trained on the watermark data. So to this end, these marks should form useful, or basically some form of patterns that are repetitive, and the model also could then memorize or learn these patterns. So we showed that this kind of patterns actually are in bitmark, where we embed very similar bit sequences, or the same bit sequences, across a given image, and then among many generated images. And if we provide such watermark images to model 2 picks up on these bitmark patterns and then memorizes them. So actually then model 2 emits the bitmark. And actually the same is for serum watermark, since we add this specific static noise for every single image, and actually every single image has this specific pattern that comes from the watermark, and the model can actually then pick up this pattern, and then model 2 is also emitting, in this case, the serum watermark. So we want exactly this property of having this radioactivity. We can then integrate this into statistical framework to trace the generated data. So in this case, we can compute, for example, for the bitmark, it was z-value. So we use statistical testing also to integrate that into framework and give us some confidence about given images being generated or not, as well as finding out if in this case model 2 was also generated on images that were watermarked with bitmark or with serum. And then the model 2 would emit one of these watermarks. And now the question is, okay, we have all of these techniques, but what is the value for both science and society? So here we would like to define the real-world impact of these methods. So right now, the EU leads the AI regulation, and then these AI regulations are expressed in the AI Act. So the AI Act is well known in the AI community. It really sets the standard, the best possible standard. Is one of the most restrictive standards in the world, how to really make AI safe, secure, more trustworthy. So by providing these tools for data provenance, we can make this law enforceable. We can ensure that our models are truly safe. This law is strict. We are not there by all means. It is still if I would say nascency to provide the methods to fulfill this requirement, but still we have this goal to which we want to go with this current methods. We want to pursue this higher level goal of, for example, watermarking the outputs from generative models in a robust way. So what we also want to achieve is that for data owners, for example, artists or content creators, we also can provide tools to test whether, for example, a given generative model was using some of their creative content. What's more also is that we want to break these data loops. So we want to ensure that the new models are not trained on generated data and can increase their quality with diverse generations. So actually this is important. For example, nowadays OpenAI provides many models, and then people generate many images, text from these models, put them online, and then OpenAI actually for the next models want to ensure that these new models are not trained on the data that actually comes from the previous models. So here what we want to avoid, for example, is that there is certain bias in the generated images, that images maybe, for example, have some hallucinations. So then we really want to avoid training the new models on this generated content. And finally, we also want to enable practical prevention of AI-produced misinformation by providing tools to identify the data sources, so to basically provide data provenance verification. So we would like to know for a piece of content if the content comes from sources like New York Times or some other press, or maybe it was just generated. So here, by tracing this content, tracing the provenance of the given content, we can then just verify where it comes from, and then have some understanding how much we should trust the given content. So in short, the goal is to provide practical data provenance tracing in the era of generative AI. With that, thank you.